Okay, so we've talked about Bronsted-Lowry theory, what it means, and how you can apply it in talking about equilibria, and also looking at structure and understanding structure of acids and how strong they are based on that proton bond. But let's move to Lewis' theory of acids and bases. Lewis' theory of acids and bases instead defines acids as the species that accepts an electron pair from a base. So here we're all talking about electrons. This is all about electrons and movement of electrons. Lewis acids accept electrons, and Lewis bases donate electrons. It's kind of the opposite here. Remember, in Bronsted-Lowry, Lewis acids donate protons, and Lewis bases accept protons. But when we talk about electrons, the acids accept electrons, and the bases donate electrons. Now, Bronsted-Lowry acids and bases are just a subset of Lewis acids and bases. You can define anything based on the Lewis acid base theory, including all of our Bronsted acids and bases. So Bronsted-Lowry is important because it helps you look at movement of protons, and movement of protons is very key to understanding acidity. But ultimately, the Lewis theory of acids and bases is going to help you the most in organic chemistry, because all of our reactions can still be defined based on movement of electrons. And once you understand why electrons move from one point to the other based on this Lewis theory, you'll understand a lot of the reactions we're going to be talking about. So here's an example of a Lewis acid, Lewis base. So remember, in this case, the base donates its electrons to an acid. Here we're forming a bond. This is a bond formation reaction, but we can still define this as the base, the donator of electrons, and this is the acid in our Lewis theory. You can also have a reaction where you have formal charges even. Again, bond formation where you have a formal charge, but still the one donating electrons is going to be the base, and the one accepting is the acid. Here's an actual example using diethyl ether and boron trifluoride. And one of the ways we also talk about Lewis acids and Lewis bases is using the words nucleophile and electrophile. So here, diethyl ether donates its electrons. That means it is a Lewis base, right? The bases donate electrons. You can see here the electrons are being donated to the boron trifluoride. We're showing that with our curved arrow. And they're making a bond. It's doing a bond formation, just as I showed in the last example. And that is called, a Lewis base can also be called a nucleophile. So the donator of electrons is the nucleophile. In this case, boron trifluoride is accepting the electrons, and thus it is the Lewis acid. The acid accepts the electrons, which is also called the electrophile. You can remember that phile means that you like something. Electrophile, remember, that means you like electrons. So if you are accepting the electrons, you like the electrons, you want the electrons. So you're the electrophile. The acid accepts and is the electrophile. And during this process, we had a new bond formation between the oxygen and the boron, where the electrons, again, came from the oxygen, which was the base, to go to the boron, which was the acid. Okay, so let's do another practice. In this case, I want you to look at our scenario. Where do we have electrons that can be donated? In this case, very obviously, our nitrogen has a lone pair of electrons. our proton actually has no electrons. It's an H+. It doesn't even have any electrons. So in this case, it's kind of obvious that our electrons can be donated from this nitrogen here. So remember, the one that is donating the electrons is the base. And the one that is accepting the electrons, our hydrogen, is the acid. Now, if you did think about this in terms of Bronsted-Lowry, you'd know that the thing that donates the proton is also what we call the acid. So it makes sense in both terms. So here, this actually forms this product. Our H, our hydrogen gets added, we make an H here, a bond here. And if we wanted to show this using curved arrows, showing how our electrons are moving, remember, from our base to our acid, you'd show the electron movement going from here to pick up our acid here. Movement of a pair of electrons to the hydrogen to form a bond. Now, again, the importance of this Lewis theory is very key to organic chemistry. We're going to be talking a lot about electrophiles and nucleophiles, which again is just the same word for the Lewis acids and the Lewis bases. Partially or fully negative atoms often are going to act as our nucleophiles. They're the ones that donate the electrons. They're the ones that have negative charge. They have electrons to give. And partially or fully positive atoms are going to act as the electrophiles, the ones accepting the electrons, the acids. They want to take electrons because they're positive. So almost all polar reactions that we'll talk about throughout organic chemistry can be envisioned as an exchange of just electrons between the nucleophile, the thing that has the electrons, is giving the electrons, and the electrophile, the thing taking the electrons. And some of the structural factors that we talked about in the Bronsted acid base strength, where we talked about proton bonds and how that affects the acidity, also can affect Lewis acid base strength. This is in the case where you do have electronegativity or polarization of a molecule, where you do have a hydrogen bond of interest that's also acting in a reaction. So it's still important to understand the structural factors we talked about when talking about Bronsted acid base strength, because they still can be applied to reactions in general. Okay, so with this in mind, let's do some more practice and look at Lewis acid bases. Here we show some chemical equations, and we want to select the chemical equation that depicts the correct movement of electrons when we react ammonia with hydrogen chloride. So first, I want you to think about, in a Lewis acid base case, which of these is more likely to be the acid and which is more likely to be the base. Remember that Lewis bases are going to be nucleophiles. They donate electrons. Usually they will have a negative charge or they'll be partially negative. You'll see electron density. And in that case, it makes sense for the nitrogen here, which again, we see its lone pair of electrons. It has a partial negative charge on it. Based on its shape and polarity, we know it has a partial negative charge. It makes sense for the NH3 to be the base in this case. I'm going to draw it here and write that. So it makes sense that this would be the Lewis base. And that means that the HCl would be the Lewis acid. It's going to accept the electrons. Okay, so that already tells us that we should be moving these electrons from here, from the base, somewhere to the acid. So if we look at our examples here, example A doesn't even do that. It moves it from our acid to our base. So we know that that can't be right. Option B has movement from the base to the acid, and so does C. And D kind of has this weird movement from the base to the middle and from the acid to the middle, which I'll tell you right now, you will never see in organic chemistry. So this option is also not a valid option. So now we're down to option B and option C, movement of electrons from the base to the acid. In this case, we're showing the electrons in option C moving from here to the proton, the H. And in this case, they're instead moving from here to the chlorine, the Cl. So now I want you to think about this Lewis acid. Think about regions where it is partially positive and partially negative. Where does it make sense for electrons to go to? And again, think about structure and polarity. And if we remember, the electronegativity and the polarity of this bond is being drawn towards the chlorine, making the hydrogen partially positive and the chlorine partially negative. So electrons are going to want to move towards the positive part, towards the hydrogen. That means that they're going to pick up the hydrogen, and in doing this, break this bond between the hydrogen and the chlorine. So it is option C that is the correct option, the option that makes sense. And if you understand these flow of electrons and what's happening here, you understand that the electrons on the nitrogen are grabbing the partially positive hydrogen, and then this bond is breaking, you can actually predict the products as well. So I implore you at home to predict what the product of this practice is and figure out, just based on the movement of electrons, what the product of this acid and base reaction would be. Okay, now for one more practice, I actually gave this practice in our Bronsted-Lowry, and we talked about which was the stronger acid and the conjugate acid, conjugate base, and how the protons were moving. And we actually showed that in this case, the proton, the H plus, was being donated from this H2SO4 to this CH3CH2OH, right? Making this the acid and this the base. We've already distinguished that. But if we wanted to define this in terms of our Lewis acid and Lewis base, we would know that that means that the base is donating electrons to the acid. So here you can see what is the item that actually bonded to the proton. It's the oxygen. That means that in this case, our electrons are moving from this oxygen to this hydrogen in an electron movement to form this new bond between the hydrogen and the oxygen. And we also know that the hydrogen dissociated, it broke a bond. And so there is electrons involved in bond breaking as well. So again, we can think about how protons are moving. So again, the proton moved from our acid to our base, which means our electrons moved in the opposite direction, from the base to the acid. Okay, so that's it for chapter 1. I really want you guys to focus a lot on this Lewis acid base theory and understanding the flow of electrons. As you can see, that's going to be very key for the rest of the reactions we'll be talking about in organic chemistry.